You guys are just reading the transcription. Did you guys, oh yeah. How come no one says anything? I'm just talking to myself. I've been talking to myself for a good 8 minutes now. Are you guys even here?
I
Yeah, we're
thought
here. We can hear
you
you.
were just preparing. I heard like little things of you writing stuff down, so I didn't want to say.
Yes, same.
Okay,
Yeah, I thought you were
but
like prepping something.
I said, I swear, I went over, I told a story for 8 minutes just to myself. I think the walls heard me, the walls of my room. They
Can you
heard
tell
this.
it again,
No, I'm not gonna.
please?
Oh no. So yeah, I began by saying that the live transcription thing, it can freeze on me again. If it freezes on me, I cannot re-enable it because I have to log out, log back in, restart Zoom. So, but I was telling the story about on like how I tutored a lot of students in the past. I told you guys that before. I had a lot of students that I tutored privately. I tutored in colleges, high schools, and I was telling a story that I had a 5-year-old Chinese student. If she was not a student, just a kid, 5-year-old. She was able to learn algebra. I taught her algebra. Such a genius. Forget about addition, subtraction, multiplication, fractions. She was able to solve for X. That kid was a genius. But then another family hired me to go over some cool things, not schoolwork, some cool things in math with their 2 sons. One of them was 10, the other son was 6. The 6-year-old was also a genius. But this is, so that, the story I said, I tried to go over the highlights right now, but this is one of the things that I taught that kid, the 6-year-old kid, okay? And it is taking 1, dividing it by 1 minus x. Okay, I'm telling you guys what power series is all about. Power series, oh, by the way, section 11.8, I also forgot to mention, because I mentioned before my mic was muted, unmuted. Section 11.7 is strategies for series. It's just a review of sections 11.2 through 11.7. And for your test, it's good that you go independently over section 11.7. It's just a review. They just review all the tests for testing convergence, divergence of a series. So just keep that in mind. Yeah, so power series. What's power series all about? This is what I taught the kid. Let's say you have, the kid knew what X means, okay? And knew what this thing meant, division. 1 divided by 1 minus X. Well, what do you do to get 1 over 1 minus X? Long division. We do 1 divided by 1 minus X. So if you haven't seen long division before in America, I think I did go over it. Probably I did. Yes, I did. You put the dividend here, divisor goes here. So you begin by dividing 1 by 1. 1 divided by 1 is 1. You put the answer here. Then you multiply 1 by 1 minus X. 1 times 1 is 1. And then we have 1 times negative X is negative X. Then we subtract. Okay, that is the long division algorithm. Divide, multiply, subtract to get the remainder. When you do 1 minus X, you get the 1's canceling out, and negative of negative X is positive X. And then you repeat the algorithm again. X divided by 1 is X. X is the quotient. I put that here, positive X. Again, multiply X by 1 minus X. 1 minus X is times X is X minus X squared. Subtract again. Okay, here X's cancel out. You get the negative of negative X squared. That is X squared. Okay, do it again. X squared divided by 1 is X squared. Multiply, you get X squared minus X cubed. And you guys do see the trend or the pattern here. The next term is X cubed. So X cubed divided by 1 is X cubed. And this thing goes forever. Okay, so 1 over 1 minus X can be written as an infinitely long polynomial. 1 plus X squared plus X cubed plus so on goes forever. Forever. All right. And that is basically a series. This thing, it's again, an infinitely long polynomial. It's a, let me do this. It is a summation of infinitely many terms. So sum of X to the power of N, where N goes from 0 to infinity. Okay. We do it that way. This is, whoops, yeah. This here, this infinite series has a name. It is a series, but there is something special about it. It has the variable X. X is the variable. And think of this as a function. It's a function of X. So I was able to write this function as a series with X. Since the series has a variable X, we call it a power series. That's what a power series is. A power series is a series with a variable. So I showed this to the kid. The mom came in the room. She saw that notation and she's like, that's enough. That's not what I asked you to teach my kid. I asked you to, I thought you're gonna teach him how to do quick multiplication. Like, no, I can't do quick multiplication. I need a tutor for that, ma'am. I need someone to teach me how to quickly multiply. I can't do that stuff. Yeah, so she was pissed, you know. Seemingly she didn't do so good in math, in calculus. But if you notice this series, this is the expanded form. Can anybody tell me what this series is? Don't think too much. What is this series? What kind of series is this? No, what is the name of this series? Of course, it's a, yeah, what?
Geometric?
It's geometric, exactly. Yes, it's geometric because every time you're multiplying by X to get the next term. The common ratio is X. When you divide two consecutive terms, X divided by 1 is X, X squared divided by X is X, X cubed divided by X squared is X. This is a geometric series, and we know the sum of a geometric series. The sum of the geometric series is first term. Well, here, first term is 1 divided by, let me write that in a different color. First term is 1 divided by 1 minus r. Here r being x. X is the common ratio. So a, that's your a divided by 1 minus r, where a is 1 and r is x. You could think of it like that. Okay, and we know that this thing converges if a geometric series converges if the common ratio is between -1 and 1. So let me write down what I said about this being a power series. This series is called a power series because it has a variable, in this case, x, okay? And since it is geometric, with a equal to 1 and common ratio r equal to x, okay? It converges for absolute value of r less than 1. Well, absolute value of r here is x, absolute value of x less than 1. All right. Believe it or not, if you take a graphing calculator, draw this function, and draw and plug in this polynomial, type in as many terms as you can. The more terms, the better. If you look at the graph of the two functions for x between -1 and 1, the two graphs are going to overlap, okay? This power series is a representation of this function, is what we say. Okay, this is a function, and we call this the power series representation of that function. Okay, so power series representation of functions will be covered in section 11.9. Okay, I'll tell you in a moment what the objective is for section 11.8. We are going to learn about different functions and their power series. For example, e to the x has a power series. I mentioned this before, I believe. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. Okay, we're gonna see why. Cosine x has a power series. It's 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial, and this thing just goes forever. Every function has a power series. Well, not every function, but we're going to talk about functions that have a power series and how to get their power series in section 11.9, 11.10. But for now in 11.8, someone is going to give us a power series like that. You don't need to know in section 11.8, we don't need to know what this comes from. For example, we're going to be given this power series, and we're not going to be told that, hey, this is the power series of that. But we are required to know when it converges. That's what we are going to determine. What values of x make this power series convergent is what we are going to answer. Okay, and we know that since this is a geometric power series, then it converges if x is between -1 and 1. That's what absolute value of x means, x being between -1 and 1. Just think about it. If you choose a number for x such as 2, if x is 2, 2 to the n, add that up, terms are going to get big and bigger. So when you add them, you get infinity as the summation. Okay, if you put 1/2 for x, you get a convergent geometric series. Jose is asking, can I get a power series for pi to the power of 2x? Ooh, pi to the power of 2x and use it to solve the p series. So the p series 1 over n to the power of 2. And ooh, man, that is crazy. I gotta think about that. To prove it. Oh, you're talking about the proof of, yes, Jose. Yeah, good. I'm not sure if you guys understand. It took me a little bit to understand what Jose's asking. Jose's asking, can you prove the summation 1 over n squared equal pi squared over 6? So he's saying, find a power series for pi to the 2x. Yeah, Jose, we could do it that way. Yep, but you got to be able to find a power series for pi to the 2x. Stuff that we're going to learn in the next 2 sections. But again, we want to know when a power series converges. Okay, but before we discuss all of that, let me properly define a power series. I have said, hey, a power series is a series that has x involved, but that is not a mathematical definition. So here is the definition of a power series. It's a little bit more involved than that. A power series is any series, okay, in the form or that looks like in the form of series or summation. We typically begin the index of a power series at 0. I know that for a regular series, we start at n at 1. But for power series, n begins at 0. In general, you are free to choose n at whatever value you want. There is no restriction on that. Who cares? That's just an index. As long as your nth term is correct, you can begin n at any value. But for a power series in this book, n begins at 0. And then we have a sub n. Please do not confuse a sub n with x, because I know I drew my x in blue earlier, but I'll tell you guys what a sub n is in a second. And then we have a sub n is called coefficients. And then we have x. X is the variable of the series minus c to the power of n. Okay, so let me expand this. Let me write out a few terms of the series or power series. So beginning n at 0, this little n is a subscript. It's just an index. So you get a0, a sub 0, times x minus c to the power of 0, and that is just equal to 1. Okay, so next term is going to be plus. It's going to be a sub 1 when n is 1 times x minus c. Okay, this is when n is 1. When n is 2, we get a sub 2 times x minus c to the power of 2. And this pattern goes forever, ever. So a sub 3 times x minus c cubed and so on. Okay, this is the general form of a power series. Here, everything has a name. We call A0, A1, A2, and so on. These are called the coefficients. A sub 0 is called a constant coefficient because it doesn't have any x attached to it. Okay, we call that, yeah, we call these the coefficients of the power series. And C is called the center. Of the power series. Okay, I'm just gonna mute everyone. There we go. All right. So this C is, for example, here for this power series, we don't have a C. C is 0. Okay. C is like a shift. Center. That center is basically a shift. You know how we learn about shifts back in pre-calculus? You have f of x minus h or f of x plus h. It's a h is a shift either to the right or to the left. For example, if you draw the function x minus 2 squared, okay, this is your function. This is a parabola shifted 2 units to the right. 2 units to the right. So your vertex is at 2. Vertex is at 2, where x is 2. That's where the vertex is. It's like the center. That point. Yeah. Yeah, we'll discuss what C is later in, I believe, section 1110. But we are going to commonly encounter series that have a center at 0, to just keep them simple. So for this series, all the coefficients, guys, all of the coefficients are 1. 1, 1x, 1x squared, 1x cubed. The coefficients are 1 and the center is 0. There is no center. Okay, but again, this is the general form of a power series. Let me show you another example. Let's say we have this power series, 1 over 0 factorial plus 1 over 1 factorial times x. Actually, guys, let me just write everything in one color for now. So 1 over 0 factorial plus 1 over 1 factorial. This is the power series for e to the x, which we'll derive later on. Okay, this is a power series because it involves x. Okay, yeah, if you notice, it can identify the coefficients. So now I'm going to use colors. We have 1 over 0 factorial plus 1 over 1 factorial times x minus, there is no center, so I can write that as x minus 0. Okay, plus 1 over 2 factorial times x minus, think of x squared as x minus 0 squared. so on. Okay, this in summation form is n going from 0 to infinity of 1 over n factorial. Look at that denominator, 0, 1, 2, 3, and they're all factorials. So that is just n. This is the variable of the sum. Y'all see that? The variable of the sum, 0, 1, 2, 3, and so on. That is the index, which begins at 0, goes to infinity. And then we have x minus center here is 0 to the power of n. Okay, so here are the coefficients of this power series are described by 1 over n factorial. That's what a sub n is. So I'm doing this example because I want you to be able to identify coefficients and the center of a power series. Okay, coefficients are everything in green, 1 over n factorial. And the center here is just 0. Okay, for this power series. Again, a power series is an infinite sum that involves x. And again, the objective is to find values of x in algebra, to find the values of x for which the power series is convergent. All right. Yeah. For example, for this power series, you ask yourself, what am I allowed to plug for this x so that the result is convergent? Okay, so for example, if you plug 1, okay, if you plug 1 for x, you get the summation of just 1 over n factorial. And we've done this problem before, didn't we? I did both basic comparison and I did the ratio test, and we concluded that this series is convergent. Convergent. See, I'm looking at the captioning and it's convergent. Oh my God, I say convergent and it writes convergence. Convergent. There we go. Yeah. So again, if you plug 1, you get convergence. If you plug 2, what would happen? If I plug 2 for x, I get the series of 2 to the n over n factorial. Okay. I don't know. What would you guys guess? Does this converge or diverge? What do you think? Yeah, convergent. You could do the ratio test on this also. We do ratio test, okay, because this involves factorials, and it would converge. It will converge. This thing, as a matter of fact, guys, this power series, let me just write it in a more neat form as x to the n over n factorial. And I'm just getting rid of the noise. If you look at that power series, on the numerator of this fraction, we have an exponential, and in the denominator, we have a factorial. X to the n is exponential and factorial. It's factorial. And we know, we have discussed the order of functions. We have discussed the order of sequence. And remember that n factorial is way more powerful than an exponential. So these terms decline really fast. Therefore, the series is convergent. And again, we could do that using the ratio test. Okay, so no matter what you plug for x, I can put 1, I can put 2, I can put -1, I can plug in -10 to the end. No matter what you plug in for x, the power series, the series is going to be, or the resulting series will be convergent. Okay, so we say that this power series converges everywhere. This power series converges from -infinity to infinity. -infinity to infinity is called the interval of convergence. Okay. Yeah. So let's discuss, we are going to discuss the convergence of power series. Okay. Yeah. If you have a power, if we have a power series, if you're given a power series, there are 3 things that can happen with that power series. Given any power series, 3 cases are possible. 3 things can happen. Okay, so we're going to discuss those cases. And it's actually, this is actually in a form of a theorem. Let me just write it out. Given a power series, so we have a sub n times x minus c to the power of n. Number 1, case number 1, says that the power series will never converge. Okay? It only converges. So we have some series that converge no matter what you plug in for x. Okay? We have some series that never converge except for one value. Okay, but let me write it down. Let me write this down. So the power series, let me call it PS, power series converges for all x. Okay, so here we say the interval of convergence is from -infinity to infinity. Okay. And there is also what's called the radius of convergence. Again, the interval of convergence is the interval on which the power series converges, the x values, all of the x values that make the power series convergent. Okay. The radius of convergence, is basically the radius of this interval. Let me discuss that. Talk about the radius. So if I have Like let's say we have an interval. The interval goes from like let's say from -2 to 2. Okay, and here is the center of that interval. Center is 0. You have an interval from -2 to 2. Think of this as the green zone. Okay, and of course the center is at 0. I believe I drew the center in blue. Okay, so here 0 is the center of the interval from -2 to 2. Can anybody tell me what the radius of this interval is?
2.
Yes, the radius is the distance from center to an endpoint, right? From here to here, we call that R. R is the radius. R is equal to 2. Okay? Yeah. Radius is the distance from center to an endpoint by definition. So for this scenario that we are discussing, radius is infinity. And we call that the radius of convergence. R is infinite. Okay? Yeah. So some power series do that. They, no matter what you plug in, just like what we discussed. For this, we're going to prove it for this power series, interval is all reals. And then we have some power series that never converge except for one value. Converges only. Can anybody tell me, think about this for a second. Can anyone point out a single value that will make the sum finite? What value of x is guaranteed to make this sum finite? Yes, Jose. Guys, think about that. What value of x is for sure going to give you a finite sum? It would be C. C. If you plug C for x, all of these become 0. All of them. They all become 0. Okay? So no matter what series you have, if you plug C, the center in it, you are guaranteed to get convergence. And you can see that in this power series, for example. Yeah, Ahmed, exactly. For this power series, guys, look, if I plug 0 for x, I'm for sure gonna get convergence. I'm just gonna be adding a bunch of zeros forever. Look at that. If I put 0 for all of these x's, these are all gone. Okay, and I end up with a constant coefficient. 1 over 0 factorials is just 1. Remember, 0 factorial is 1. Okay, 0 factorial is 1. So all of these go away. They all vanish, and you get that as the sum, the constant coefficient. So the power series converges only for x equal to c, meaning that there is no interval of convergence. Only a single value makes the power series converge. Yeah, so some power series never converge except for when x is a center. Yeah, here we say that again, the in this case, the value of the power series becomes the constant coefficient. You know what? I'm not gonna write that. That this could confuse people later on.
Yeah, Professor, I think your screen is frozen.
Oh, is it? See, that's what I was talking about, the captioning, the transcription thing. So, yeah, I have to log out, log back in, guys. Yeah, I'll be back shortly. Don't go anywhere. Okay, so I can't enable. Wait. How do I disable that now? Can you disable the transcription here? Let me see if I can disable it. I had to disable. Sorry, guys, I had to disable. Does anyone have a hearing problem here? If you have a hearing problem, please, guys, please send me a private message, and we'll do. We're gonna do something about that, about this, the captioning. But yeah, let me know. Let me know if someone here has a difficult time hearing me. Please let me know. But for now, I can't do the live transcription again because it's gonna freeze. Okay, sorry about that. Okay, so power series converges for x equal to c. We can, yeah, SMC, I think they have someone that can do the transcription for us. Yeah. Or maybe I could switch computers. I don't know. I don't know what's going on. But the power series converges. So as we were saying, for x equal to c, again, there is no interval of convergence. So here we say the radius of convergence. Again, we call that capital R is equal to 0. There is no radius because there is only a single point. Unlike this problem, unlike this, you have an interval of values. Here, it's only a single point for which the series converges. So here it's all reals. R is infinite here. This is C. And here it only converges for x equal to c. Maybe I should, okay, what I'm gonna do is I'm gonna draw the interval as a green interval because think of that as the green zone, okay? Green zone. So here the only green zone is C. All right. Yeah.
Professor, just a
Uh,
quick question. So
yeah.
you see how you found you put like the -2, 0, and 2 on the interval. How would you
Yeah.
find the -2 and 2?
Oh, yes, we'll do that.
Okay.
I haven't yet discussed the finite intervals.
Okay. Okay.
I haven't yet done that. So I just drew drew an interval, and to tell you guys what radius of that interval is.
Okay. Okay.
Okay, yeah, we haven't done an actual problem. I'm just discussing cases, what could happen. And then there is a third case, which is what Ahmed is mentioning. And this says that there is going to be an interval of values for which the series converges for. Okay, so 3 cases. The power series converges no matter what. A power series converges only for one value. And 3 says that the power series converges over a finite interval. Okay. Yeah, so this says that there is a radius r greater than 0. There is a number, a radius like 2. Okay. Such that the power series converges for absolute value of x minus c less than, I'll tell you what this means in a second, less than r. Okay, so this says, I will draw this in a second. This says that as long as you are within, that's what this means, being within r distance of c, as long as we are within r distance of c, the power series converges, okay, and diverges everywhere else outside of that interval. That means being out of that interval, not being within, okay? So here is the drawing. This is the x-axis, guys. So assume the center is C, C is whatever. It's commonly 0, but C could be any number. So there is an R, meaning that if I go R distance away to the right, or go R distance, well, away, it could be right or left. Okay, so this point is C plus R, and this point is C minus R. Okay, this interval here, the green zone is what this inequality means, what this absolute value inequality means. Okay, so if I translate this for you guys, so meaning power series converges for x being between, I'm rewriting the meaning of this absolute value inequality. If you hate absolute value inequalities, this should help. You shouldn't. But the meaning of this is x being between C minus R and C plus R. Okay, So being between these two values, as long as x is between those two values, then the power series is converging. And if it's outside, so here, the less than means being within, and greater than means not being within, being outside. So here is the red zone, divergence. Okay, so here power series diverges, here it's divergent, and over the green zone, it's guaranteed to converge, for sure. Am I missing something from this picture or this statement? What do you guys think I am missing from the statement? I did not discuss the convergence or divergence at certain locations. Yeah, there is something that I left out from this picture. So I have, oops, here divergence, and here convergence. What?
If it
Yeah.
converges or diverges at C minus R and C plus R?
Yes, yeah, these points. The theorem here doesn't say anything about these endpoints. And it turns out exactly what you said. Who said that?
I did.
Yeah, Anthony, good job, Anthony. The power series, the theorem doesn't tell you, can't tell you what happens at those endpoints. So we're gonna put a question mark at those endpoints. Here and here, the power series may converge or may diverge at x equal to C minus R or x equal to C plus R. You know how you do the ratio test? And the ratio test, the limit of the ratio is 1. The test is inconclusive. That's exactly what we are dealing with over here. We're gonna see that. But again, we have certain power series that sometimes converge. By sometimes, we mean it's converging between these two endpoints, okay, and diverges for sure, as long as you're not within, and anything could happen at those points, okay? The theorem doesn't tell you that for sure, the power series will converge at those. There is no theorem that says that we have to include the endpoints, okay? Anything can happen at the endpoints. So this is the more complex case. Of course, it's gonna take me about 15 minutes to do an example for case number 3. But let me do an example with one of the other 2 cases. Let's go with this power series. Okay, here we want to find the radius and interval of convergence. I don't even think I have enough time to finish this problem. But remember, guys, so this is how you are gonna begin approaching the problem. Okay, we know that a series is convergent if it's absolutely convergent. A series converges if it is absolutely convergent. So here I have to check, guys, I have to check for absolute convergence. You know why? It's because a power series is not always a positive term series. It's not. Here, x could be any number. It could be negative, it could be positive. So if, for instance, x is a -1, you get -1 to the end, this becomes an alternating series. Okay, that's why you have to check absolute convergence. All right. Check for absolute convergence by evaluating the limit. Then goes to, we're gonna do the ratio test. Okay, we're just gonna do ratio test for all of these problems. Limit as n goes to infinity of u sub n plus 1 divided by u sub n in absolute value. Okay, do that limit in absolute value and you are checking for absolute convergence. All right, and your u sub n is that. Let me see if I can quickly. We're going to discuss the problem later in more details, but here is my u sub n. Okay, well, I'm not going to call that a sub n because a sub n is 1 over n factorial. Just call the nth term of a power series whatever you want. Just don't call it a sub n. All right, so u sub n plus 1 is x to the n plus 1 divided by n plus 1 factorial. And then multiply that by the reciprocal, which is n factorial over x to the n. And then remember the procedure. You're gonna expand or factorize a sub n plus 1. X to the n plus 1 factors to x to the n, and x, n plus 1 factorial is n plus 1 times n factorial. Leave it at n factorial because the n factorials cross cancel. Okay, those are gone, x to the n's are gone, n factorials are gone. We end up with limit as n goes to infinity. Okay, and n plus 1, guys, n is a positive number. N goes to infinity. N is a positive number. So this n plus 1 shall be positive no matter what. I can take this out of the absolute value. N plus 1 is always positive. No absolute value needed. My handwriting. Okay, but x, since x is a variable, I don't know if x is positive or negative, I need to keep that in the absolute value like that. Okay, so this is the limit of the ratio. And in order for the power series to converge, we want this limit to be less than 1. Remember the ratio test? Ratio test says that the limit must be less than 1. Okay? You have this weird inequality, guys. I'm so sorry, I'm going over time. But if you have to leave, go ahead. I will re-explain this next time. If you gotta go, you can go ahead and leave. But if to solve this inequality, I'm trying to solve for x. That's what we are solving for. We are solving for x. X is the unknown. Okay, so solve for x. Get rid of this n plus 1. Multiply both sides of this inequality by n plus 1. I'm going to put the n plus 1 on the right hand. N is positive. The inequality doesn't change. Okay, now since I put the n plus 1 on the right, I multiply by n plus 1. That is gone. I have to put the limit on the right hand side. Okay, and of course, limit of n as n goes to infinity is infinity, so we get absolute value of x less than infinity. This means x is all real numbers. That's what absolute value of x less than infinity means. X is between negative infinity to infinity. So x is all reals. That's what it means. X is all reals. Notice that if you were to take the limit here, if you just leave it like that, take the limit, this goes to 0. Okay, this goes to 0 because n grows in the denominator, x divided by that is 0. You get 0 less than 1, which is true for all x. This is true for all x. You could think of it like that. But this is the interval of convergence. So the radius is infinity. Power series converges for all x. Okay. Yeah. So for all of these problems, we just do check for absolute convergence by running the ratio test. Ratio test. Okay. Do the ratio in absolute value. It's the same as checking for absolute convergence. And you want it to be less than 1. Okay. And that will tell you what x is. Great, guys. I will see you tomorrow.
Tomorrow.
Well, not tomorrow. Sorry. Tomorrow is Veterans Day. Any veterans here by chance? No veterans? A happy Veterans Day. Guys, enjoy your weekend. Don't forget to study, okay? I gave you this wonderful chance to study more. Take advantage, please. If you have questions about anything math related, email me, please, okay?
Thank you, Professor.
Guys, have a great day. Bye.